Here is the punctuated text. Folks, this is dim and it has tremendous mass. The fact that 3 conclusive pieces of evidence make what more, it's little not too far off right, embroiling a super monstrous dark opening. Space can be unnerving to ponder. The risks that sneak inside the tremendous territory of the room can be alarming. While this applies to the whole idea of room investigation, the one section that has forever been fascinating and alarming simultaneously is dark openings. These monsters of force have been the subject of innumerable investigations all across the globe. Researchers have been attempting to sort out exactly what dark openings truly are and what lies in them. In any case, each of those changes now. Neil deGrasse Tyson recently uncovered something gigantic. Our dark opening is less huge than the one in the focal point of the Andromeda world, our closest large world. So we have dark opening jealousy. I figure we do. We at long last see what's inside a dark opening, and well, all of it may very well knock your socks off. So join us as we take you on this intergalactic excursion and respond to quite possibly history's most posed inquiries. What is a dark opening? Made from an enormous blast, the dark opening's mass is gathered in a minuscule locale, creating a gravitational force so intense that nothing, not even light, can escape from it. Once something is in there, it's going to remain in there forever. These forces of energy come in different sizes, ranging from heavenly dark openings, which can be a few times the mass of the sun, to supermassive ones that exist at the centers of galaxies and can have millions or indeed, even billions of times the mass of our sun. Researchers have noticed the impacts of dark openings indirectly for quite a long time now, and with each piece of information, we uncover many privileged insights. Despite the fact that it appears as though they're so enormous and strong that they couldn't in any way, shape, or form have a history, they truly do. Dark openings don't simply exist in space. They're made. They need the leftovers of huge stars that have depleted their atomic fuel to be conceived. These stars go through a cosmic explosion blast, a staggering event that marks the finish of their lives. During a cosmic explosion, the external layers of the star are savagely removed into space, while the core undergoes a gravitational collapse. Not all collapses are the same. Assuming the core's mass is a few times larger than that of our sun, the force of gravity overpowers all remaining forces, causing the core to implode inward. This collapse is so extraordinary that it packs the mass into a minuscule volume, creating an object with a gravitational field so strong that nothing will be able to escape its grip, thus creating a dark opening. The size of a dark opening is determined by its mass. Heavenly dark openings, which are the most commonly known type, have a mass range from a few times to many times that of our sun. At the center of a dark opening lies the singularity, a region of boundless density and space-time curvature. According to our current understanding of physics, the laws of nature break down, and our customary theories can't fully explain what occurs inside the singularity. To truly comprehend the nature of singularities, we need to think outside the box. In the realm of physics, a singularity refers to a point in space-time where certain quantities become infinite or undefined. These singularities appear in various theoretical settings, such as at the beginning of a growing universe, commonly known as the Big Bang singularity, and inside dark openings. When we study the Big Bang singularity, a central challenge emerges. According to theory, the universe started from an incredibly hot and dense state around 13.8 billion years ago. However, as we rewind time toward this initial state, the conditions of general relativity, which govern the behavior of gravity, break down. This breakdown implies that our current understanding of physics can't fully describe the conditions at the moment of the Big Bang. Resolving this issue requires a theory that combines general relativity with the principles of quantum mechanics. Dark openings contain singularities at their centers. These are regions where the gravitational force becomes infinitely strong and space-time is highly curved. According to general relativity, matter and energy that fall into a dark opening reach its singularity and become infinitely compressed. This concept is beyond our current understanding of physics. The challenge of singularities has inspired researchers to look for a theory of quantum gravity, which aims to unify the principles of general relativity and quantum mechanics. Quantum gravity seeks to provide a framework that accounts for the behavior of spacetime on both cosmic and subatomic scales. A theory like this could potentially offer insights into the nature of singularities and how the universe truly works. One approach to resolving the issue of singularities is the theory of loop quantum gravity. This theory proposes that at tiny scales, spacetime is quantized, meaning it consists of discrete, indivisible units. These fundamental units are often referred to as loops or spin networks. In loop quantum gravity, the concept of quantization is applied to spacetime itself. This means that spacetime isn't considered a continuous and infinitely divisible entity, but rather a collection of discrete elements. These discrete units of spacetime are often seen as interconnected loops or networks that represent the fundamental structure of the fabric of the universe. Within the framework of loop quantum gravity, singularities associated with dark openings and the Big Bang could be resolved. One of the key insights of this theory is that at minuscule scales, the discrete nature of spacetime prevents the occurrence of infinite densities and curvatures that result in singularities in classical general relativity. For example, in the context of dark openings, loop quantum gravity proposes that as matter collapses toward the core, the spacetime fabric becomes increasingly minuscule. This size prevents the matter from reaching an infinitely dense singularity. Instead, the collapsing matter encounters a quantum bounce near the core, where it rebounds and begins to expand again. This scenario leads to the formation of a new spacetime region within the dark opening, often referred to as a quantum dark opening or a bounce region. Heavenly dark openings are the most commonly observed type of dark opening in the universe. They are formed through gravitational collapse toward the end of a massive star's life. Once a massive star exhausts all its nuclear fuel, the outward pressure generated by nuclear reactions can no longer balance the force of gravity pulling inward. The gravitational force becomes dominant, causing the star to collapse under its own weight. This collapse results in the formation of a heavenly dark opening. As the star collapses, it becomes incredibly compact, compressing a large amount of mass into a tiny volume. As a result, heavenly dark openings typically have a mass ranging from a few times to many times that of the Sun. Despite their mass, they have remarkably small sizes. Their diameter is just a few kilometers, which demonstrates how incredibly dense they are. The immense density of a heavenly dark opening leads to the formation of an event horizon, a boundary beyond which nothing, not even light, can escape. This event horizon marks the point of no return, where the gravitational pull of the dark opening becomes so strong that any object or information that crosses it is trapped forever within the dark opening. Then we've got intermediate mass dark openings. While the exact mass range for intermediate mass dark openings is still something researchers need to put through more exploration and refinement, they are generally thought to have masses ranging from thousands to hundreds of thousands of times that of the Sun. These massive entities occupy the central regions of most galaxies, including our own Milky Way. They hold significant gravitational influence over their cosmic surroundings and have a substantial impact on the evolution of galaxies. The formation of supermassive dark openings remains an active area of research and is still not fully understood. However, even then, lots of various theories have been proposed to explain their origins. One prominent hypothesis suggests that supermassive dark openings grow from smaller dark openings through a process called accretion. According to this idea, as matter, such as gas, dust, and stars, accumulates around a dark opening, it forms a swirling disk known as an accretion disk. The dark opening's immense gravitational force draws material from this disk, causing it to spiral inward and eventually merge with the dark opening. Over vast time frames, this continuous accretion of matter allows the dark opening to grow to a supermassive scale. During the accretion process, tremendous amounts of gravitational potential energy are released as the matter falls into the dark opening. This released energy powers some of the brightest and most powerful phenomena in the universe. But away from all that are charged dark openings, which represent a captivating variety of dark openings characterized by the presence of an electric charge. There are two main types of charged dark openings: Reissner-Nordström dark openings and Kerr-Newman dark openings. Each type exhibits distinct properties that are formed from the interaction between the dark opening's charge and other factors, such as spin. Reissner-Nordström dark openings are charged but non-rotating. They are described by the Reissner-Nordström solution in the framework of general relativity. The charge of these dark openings affects the behavior of their gravitational field. However, in terms of their overall structure, Reissner-Nordström dark openings are similar to uncharged dark openings. They have an event horizon, but the size of the event horizon for a Reissner-Nordström dark opening depends on both its mass and electric charge. On the other hand, Kerr-Newman dark openings are charged and rotating. They are described by the Kerr-Newman solution in general relativity. The combination of electric charge and rotation introduces unique phenomena associated with these dark openings. One of the notable effects is called frame dragging, which occurs because the rotating dark opening drags and twists the surrounding spacetime. Kerr-Newman dark openings have both an event horizon and an inner horizon. The inner horizon is a boundary within the event horizon where the gravitational and electromagnetic forces become extremely intense. This leads to complex dynamics within the dark opening. The presence of an electric charge in charged dark openings introduces interesting effects. Charged dark openings have regions called the inner horizon and outer horizon, which are distinct from the single event horizon seen in uncharged dark openings. The inner horizon lies closer to the singularity, while the outer horizon is the boundary that separates the dark opening's gravitational influence from the rest of the universe. The electric charge also affects how charged dark openings interact with their surroundings. For example, charged particles are influenced by the dark opening's electromagnetic field, leading to unique patterns of motion around these objects. This interaction can affect how matter accretes onto the dark opening and how it emits radiation. Dark openings are very interesting, and some are more interesting than others. Quantum dark openings are just like that. They refer to hypothetical concepts that arise from attempts to understand the behavior of dark openings within the framework of quantum mechanics. The combination of quantum mechanics and general relativity remains an area of active research, and quantum dark openings are part of this ongoing exploration. Dark openings, in particular, exhibit behaviors that challenge our classical understanding of space, time, and gravity. In the classical description of a dark opening, it contains a singularity, a region where matter is infinitely compressed and gravitational forces become infinitely strong. However, quantum mechanics suggests that the classical picture of a singularity might not be entirely accurate. One of the central ideas in the concept of quantum dark openings is that the singularity could be replaced by a quantum state that prevents the occurrence of infinite densities. Researchers have proposed various scenarios and models to describe quantum dark openings. One possibility is that as matter collapses toward the core, it undergoes a quantum bounce, where the collapse is halted and reversed due to quantum effects. This bounce could create a new spacetime region within the dark opening, avoiding the classical singularity. Quantum effects could also impact the event horizon of a dark opening. The event horizon is the boundary beyond which nothing can escape the dark opening's gravitational pull. In classical theory, the event horizon is a well-defined boundary. However, in the context of quantum mechanics, the event horizon might have a more nuanced structure due to quantum fluctuations and effects. Another intriguing aspect of quantum dark openings is the potential for information preservation. In classical physics, information that falls into a dark opening is thought to be lost forever beyond the event horizon. However, quantum mechanics suggests that information might be preserved through processes like Hawking radiation, a quantum phenomenon where dark openings emit particles due to quantum fluctuations near the event horizon. This raises the question of whether information could eventually escape a dark opening. As researchers continue to explore the intersection of quantum mechanics and general relativity, new insights into the behavior of dark openings and the nature of spacetime are being revealed. Overall, quantum dark openings remain a theoretical concept, but they offer a window into the fascinating world of quantum gravity and the potential resolution of long-standing mysteries in physics.